Hello, my name's Chelsea and this video is part of a series of A-level content that is all about learning differentiation. The image of the worksheet in this video, as well as other maths related content, is over on my Instagram page because I love me some numbers. Okay, you all know the YouTube drill now. This content is free from me to you. Therefore, it'd mean a lot to me if you hit that like button, press subscribe and wait for it, go follow me on Instagram, just so I know that maybe this is quite useful and I should continue doing it. Thanks for watching.
Worksheet 4 for differentiation, and the topic is stationary points. So visually speaking, what are stationary points? Stationary points are points on a curve where the slope is flat. So when I think of stationary points, or when I'm explaining them, I like to use the roller coaster analogy. So if you remember from previous worksheets, you know, a curve going down like this would have a negative gradient. A curve going up like this would have a positive gradient. And where the curve is flat, horizontal, that would have no gradient. Stationary points are points where the slope or gradient is zero. So when looking at this roller coaster, we have a stationary point here, i.e. it's the point where the gradient has gone from negative to zero and then to positive, i.e. it's zero here. This is a stationary point. And then up here at the top of the roller coaster, the gradient has gone from positive to zero and then to negative as it goes down. So again, here is a stationary point. It's where the slope is flat, or you might also say the gradient is zero. And then we also have stationary points that look a bit like this. And it is when the gradient is going up and up and up, goes to zero, and then continues going up and up and up. And you can have it the other way around, like the gradient could go down, it could be negative, it goes to zero, then it goes negative again. So when you're thinking about stationary points, think about this roller coaster and think of this guy here as the maximum stationary point, this guy here as a minimum stationary point, and this guy here as a stationary point of inflection. Let's just go over what I've just said, but in maths talk. So when you see a definition for a stationary point, you'll see something that looks a bit like this. The point x is said to be a stationary point of the function f of x if the first derivative is equal to zero, when it is evaluated at that value of x. So if someone gives you a function and says, find the stationary points of that function, what you would do is you would differentiate. So you would find the first derivative and you would set that to zero and see what values of x let this relationship occur. As I've already touched upon, stationary points have different natures. We went over this stationary point and I said it was a minimum. It's down low, it's like a happy face. And this stationary point up here is a maximum. It's got like an unhappy face. You can actually find the nature of stationary points. And the way you find them is by looking at the second derivative of a function. So when you have two dashes here, that means second derivative. And the way you get to that is really easy. You differentiate your function twice. So the formal definition for the nature of stationary points, we say if x is a stationary point of the function f of x, then it is a maximum stationary point if the second derivative is less than zero for that value of x. And it is a minimum stationary point if the second derivative is greater than zero for that value of x. Now, a stationary point is said to be a stationary point of inflection, like these weird stationary points, if you find that the second derivative is actually equal to zero for this value of x. And then what you do in questions is you usually look at, does the second derivative change sign either side of the x? And this is proof that that point of x is a stationary point of inflection. So let's go over some examples of these. Okay, first example here. Let me scroll down a little. Find the coordinates of all of the stationary points of f of x is equal to 3x cubed minus 36x minus 10. Okay, first things first, you're wanting to find stationary points. You must think back always to the definition. To find a stationary point, you need to find the value of x such that the first derivative is equal to zero. So probably the first thing you need to do is actually find the first derivative. We need to basically differentiate our function. So here it is. We've taken the function up here and we've differentiated it to get 9x squared minus 36. Right, next thing we need to do is we need to find the values of x such that the first derivative is equal to 0, i.e. this guy is equal to 0. Well, if the first derivative is equal to 0, that must mean that this is equal to 0. Therefore, we need to actually solve this equation here for x, i.e. we need to find the values of x such that this side of the equation is actually equal to 0. And here we go. We find that x is equal to plus or minus 2, i.e. when we put plus 2 into this equation, it results in 0. It's equal to 0. Similarly, if we put minus 2 into this equation, it's equal to 0. So the first derivative is equal to 0 for x is equal to 2 or minus 2. Therefore, we can say that x is equal to 2 or minus 2 is a stationary point of our function. Now the question is actually asking for the coordinates of the stationary point. So we need to find the corresponding y coordinate that goes with x is equal to plus or minus 2. So let's do that. So we just say when x is equal to 2, what is y? So we plug 2 into there. And similarly, when x is minus 2, what is y? And we plug minus 2 into there and we get the results. And therefore, we get the full coordinates of the stationary points as 2, minus 58, and minus 2, 38. So that's the first part of the question done. The second part of the question is asking us to determine the nature of the stationary points. Remember, coming back here, if we want to determine the nature, i.e. is a stationary point a maximum, a minimum, or even a stationary point of inflection, what we need to do is we need to find the second derivative and see what sign it is, i.e. is it less than 0, greater than 0, or even equal to 0. So first things first, we need to find the second derivative. And here it is. We've got the second derivative, basically differentiated the first one. So we took the first derivative and differentiated again to get the second derivative. And we get it as 18x. So what we need to do is, in order to determine the nature of these stationary points, we need to put in our values of x again into the second derivative and see what the sign of the second derivative is. So when x is equal to 2, the second derivative is 18 times by 2, which is 36, which is greater than 0. Therefore, this stationary point must be a minimum, i.e. it looks something like this one. Now when x is minus 2, the second derivative evaluated for this value of x is equal to minus 36, which is, ooh, look at that. That's wrong, isn't it? That should be the other way around, is less than 0. So, maths, we all make mistakes. Less than 0. So this stationary point is a maximum. Therefore, it looks something like this one here. Therefore, 2 minus 58 is a minimum stationary point of our function, and minus 2 and 38 is a maximum stationary point of our function. Here we go, I've just changed that sign now. So minus 36 is actually less than 0, guys. Right, let's look at a second example. So show that y is equal to x cubed minus 3x squared plus 3x has a stationary point of inflection at x is equal to 1. So again, remember your definition. A stationary point of inflection is first and foremost a stationary point. So we need to prove that x equals 1 is a stationary point to begin with, and then we'll just look at what nature it has. So in order to show that something's a stationary point, we need to find the first derivative of the function. So we need to differentiate. And here we go. We've differentiated y to give dy by dx is equal to this here. In order to show that x is equal to 1 is a stationary point of this equation, what we need to do is show that if we substitute 1 into here, we get 0. I didn't actually do it like that. I just solved this for 0 and showed that the solution is 1. But you could just put 1 in here and showed that it is equal to 0. So here we go. I've taken this equation here, set it to 0. I've solved it for x and I found the solution is 1. Therefore, I've proved in a bit more long-winded way that x is equal to 1 is a stationary point. Now, the next bit of the question, well, still the question, is actually saying show that x is equal to 1 is a stationary point of inflection. So we need to think about what was the definition for a stationary point of inflection. We had that the second derivative must be equal to 0 and that the second derivative changes sign. So here we found the second derivative as this. When we substitute x is equal to 1 into this, we get that the second derivative is equal to 0 because we get 6 minus 6 is 0. Now, assuming x is greater than 1, you can either do this by eye or just assume a value that's greater than 1, so 2 for instance. We'll see that the second derivative must be greater than 0. So if this is 1, we get 0. If this was, say, 2, we'd get 6 times by 2, which is 12 minus 6, which is 6, which is greater than 0. So you can kind of see for all values of x greater than 1, the second derivative is greater than 0. Similarly, for x less than 1, you can think of a value less than 1, such as 0, plug it in, we get minus 6. You can see that for x is less than 1, the second derivative is less than 0. So at x is 1, we get the second derivative as 0. At x is greater than 1 or less than 1, we get different signs for the second derivative. Therefore, we have proved that x equals 1 is a stationary point of inflection. And it will look something like this. Or maybe it might be the other way around, I don't know. But yeah, like these ones. As usual, I've just put some questions together here. The answer to these can be found on my Instagram page. I hope this is helpful. Thanks for watching.